All right, so here you are for the much anticipated energy lecture 6. All right, so this is going to be our first lecture for chapter 13, which deals with renewable energy and conservation. Okay, so we'll start looking at some of these alternative forms. So first of all, we're going to talk a little bit about solar energy. Most of all our alternative and renewable energy is either directly or indirectly solar. Okay, so you could kind of picture we have solar energy, which takes many forms, and we have direct and indirect. Okay, and I'm sorry about the writing there. So we have direct solar energy versus indirect. That says indirect, you just have to trust me. Okay, and then within our direct solar energy, we have what's called passive and active. Okay, so with our direct solar energy, which is what most of us think about with solar energy, we can use that passively, and that's something as simple as south-facing windows to use natural light, or getting some passive heating from just regular sunshine. That's what we mean by passive solar energy, and we'll talk about that more in just a moment. But there's also active solar energy, which is when we talk about solar energy, typically you guys are probably thinking of solar panels. That is active solar energy because we do have to have some sort of mechanical device. Now the indirect solar energy would be things like wind and hydropower, because those are powered by processes powered by the sun, allow us to then get wind and the water cycle, which then we use those processes. That's why that's called indirect solar energy. All right, now looking at a map of the U.S. here, we can see that the potential to use solar energy varies based on location, right? So here, of course, in the desert Southwest, we've got our largest solar potential. No big surprise there. Parts of Washington, right down here where Walla Walla and Tri-Cities are, we've actually got some decent solar potential in this area. Moderate, I guess you'd say. In other areas where you could still use solar energy, but probably not get as much bang for your buck. All right. So when we talk about using solar energy for heating buildings and water, typically these are design features built in, and not necessarily high tech. It could be something as simple as the orientation of your house relative to the direction sunlight comes from, and so on. And I'll show you some examples of that. But passive solar energy refers to the system of putting the sun's energy to use without requiring mechanical devices to distribute and collect heat. All right. So like I mentioned before, south-facing windows, using well-insulated buildings, attic vents, and overhangs and solar sun spaces. These are all design features, low tech, things that we could have been doing for probably centuries now. Okay, because they're such low technology. So here's the book gives a nice little diagram of ways that we can use passive solar energy. All right, so we have a south-facing window, right here, which is double paned to prevent heat loss at night. Okay, now notice this overhang right here. These have to be properly sized based on your latitude. So ideally, the south-facing windows would have overhangs that actually shade them during the summertime. All right, so that we're not getting that direct sun on the time of year where we don't want that passive heat. But the overhangs can't be so large that they block that winter sun, in that we can actually use that lower horizon sunshine to directly heat your house, or at least supplement some of the heat that you're getting. Okay. Now, in order for this system to work, though, we have to have very, very good insulation and so on. But this is an example of how a passive solar house would be built. All right. Now, when we talk about active solar energy, these are a little bit higher tech, although we've had technology to use active solar energy for quite some time. But we do have to have some sort of mechanical system for collecting and absorbing the sun's energy. And so in the case of this water heater, right, we have pipes in some sort of dark colored box to help collect that energy. And we can actually heat water up relatively hot. That goes to a heat exchanger, which then delivers hot water to your hot water tank. Okay. And typically, because we're not always going to get good direct sunlight, we might not be able to heat your water enough. So most of your solar hot water heater tanks have a backup heater. So maybe you only raise it a few degrees up a little higher to get it to whatever level you want it. But it does require less energy from your own hot water heater if you can heat it somewhat with the sun using a solar hot water heater. And then in the summertime, when you do get that direct sun, your backup heater probably doesn't have to do any work at all. These are not particularly expensive, but it is considered active solar energy because we have to use some sort of mechanical device. All right. As far as electricity generation goes, it's usually done one of two ways using solar energy. One of them is called solar thermal. All right. This is a more efficient process than solar photovoltaic, although it's more expensive and it has to be done on like a kind of utility grade scale, unlike photovoltaics, which can be done on pretty much any scale. Okay, but with solar thermal electric generation, it's concave mirrors, right, focusing on a pipe. That pipe is typically filled with oil as opposed to water, and the reason they use oil is it can be heated to a much higher temperature than water before it starts to boil and create high pressure. All right. They would use the heat from that oil just to power then a steam turbine system, much like we talked about with coal and nuclear. All right. It is, like I said, more efficient than photovoltaics, more expensive, although there's no air pollution and no contribution to global warming or acid precipitation with solar photovoltaic. Now, what you guys are probably more familiar with, though, are these actual, you typically hear them called solar panels, right? And these are what they call solar PV for photovoltaic. And these are different because they're not using heat to then produce steam and spin a turbine. These actually take photons from the sun and convert those photons directly into an electric current. Okay? So sunlight gets directly converted into electricity. Now, the most common models that are out right now, although they are improving this, are really only about, 15% efficient. And that's just the materials they use only absorb about 15% of the sunlight and are able to convert that to electricity. Now, some of the benefits with these is they can be used on any scale. They can be used for something as small as a battery for a calculator, or they can be used all the way up on the utility scale to produce hundreds or thousands of megawatts of electricity. So that's the biggest benefit. And the reason these are used probably more commonly than solar thermal is the small scale capabilities. You can just put them on people's rooftops. They don't have to have a large power plant. So the costs associated with them can be much, much smaller. All right, so why don't we use solar energy more often? Well, first of all, we can only produce power during daytime unless we're able to store that energy with some sort of backup, like a battery, for example, which is proving to be a big challenge for us. Requires a lot of space. So in the case of photovoltaics and solar thermal, a large footprint is needed, although it is worth stating that we can throw photovoltaics on top of space that's already being used. So we can put them on rooftops, on the medians of highways, over parking garages, and so on. So it's not as big of an issue with the photovoltaic. But solar thermal, you're going to have to put that out somewhere far away because you need one large, wide open space for that to make that work. And in the short term, they are more expensive than fossil fuels. Although if you take kind of the whole lifetime, current photovoltaic panels, for example, are expected to last upwards of 100 years. All right. So once installed in over a 100-year period, definitely cheaper than coal or natural gas. It's just kind of an upfront expense that lots of people don't find favorable. Let's see. Generating electricity at the utility scale is challenged more for the photovoltaics. And there's lots of variables involved with how much electricity you can get out of photovoltaics. Cloud cover, the angle of sunlight, the time of day, all these things make it a little bit more of a challenge. Now, the book is a little outdated. in terms of cost. As of 2013, which is kind of the best data I could find for now, most of our wind and solar technologies are very much competitive with coal. So if we look at coal and advanced coal, right, we're looking at 10 to 12 cents per kilowatt hour. Natural gas, right, about 8 cents per kilowatt hour. The with CCS, that's with carbon capture and storage, by the way, so to help augment the issues with climate change there, right? So typically that would mean pumping it underground or something like that. So if we look at the cost there, now let's compare it with photovoltaics. Photovoltaics still run a little more expensive than our traditional coal or natural gas plants, although not much more so. Just a few short years ago, solar PV was up over 20 cents per kilowatt hour. So it's a nice drop as production has come up, becoming much more competitive. And in fact, that 12 cents per kilowatt hour is an average. If you go to the desert Southwest, like in Arizona, solar photovoltaic is actually cheaper than running off fossil fuels, which is kind of a new advancement. Hydropower still runs pretty darn cheap, about 8 cents per kilowatt hour. Wind has definitely dropped as well to only be operated at 7 cents per kilowatt hour. So lots of people, when they talk about costs of these alternative energies, are probably operating off some outdated data, although that's excusable because the public information tends to lag a little behind. But cost really isn't an issue with photovoltaics and wind. It's really how much energy we can get, and can we get it when we want it. That's more of an issue. All right, so indirect solar energy. So again, we're talking about processes that use the solar energy originally. So again, things like wind, which are driven by atmospheric currents, and those atmospheric currents are driven by changes in solar energy, right? The hydrologic cycle, which we use for hydropower. Evaporation, that whole cycle relies on solar energy. Biomass, right? So plants, as you know, use solar energy for photosynthesis in order to grow. So those are what we call those indirect solar energies. But still, ultimately, that energy source is the sun. All right, so biomass, for example, plant material used as food. So this is a pretty common thing. Lots of you guys probably have wood stoves in your house. You are using biomass energy. So wood, crop waste, sawdust, whatever, pellet stoves, for example, are all using biomass as a form of energy. Typically, we would use that as a heat source. That's the most common use. All right. We already talked about the photosynthesis thing. Now, is biomass energy renewable? There's kind of a spectrum there, but theoretically, yes. If you're regrowing plants at the same rate in which you use them, that is a renewable resource, as long as the rates are equal. Okay. And we can also use biomass now to convert to a liquid fuel that we can use in transportation. So most of you know now that gasoline is at least part ethanol, usually around 10% or so. Biodiesel, which is basically using vegetable oil, can be used as a diesel substitute. All right, and these would be considered renewable fuels, again, because we can grow the plants to produce them. So what are some advantages of biomass? Definitely reduces dependence on fossil fuels because we can directly replace our fossil fuels with biomass fuels. It often uses waste materials. So there's new technology into using, like, let's say we grow corn for food, right? Using the cellulose from the corn stalks to then produce ethanol. So we can use crop wastes more efficiently. And of course, we can have no net increase in atmospheric CO2 because for when we burn the fuel from the plants, theoretically, we are regrowing plants, which take that same amount of carbon back out of the air. Okay? Now, disadvantages. If we start using agriculture for energy, we're going to have to convert more land over to agriculture. Okay? Because we're still going to have to eat. And so if our food is now becoming energy and fuel, we're going to have to convert more land over for agriculture so that some of it can be used for fuel and energy, and we can still grow, of course, food for ourselves. And doing so would then lead to things like deforestation, Desertification and soil erosion are things we'll talk about in a later chapter, but also some disadvantages there. Wind energy. Hey, you guys should know all about this because we see it all around us. In areas where wind is common or pretty much a daily affair, wind energy is a very, very good option. Lots of people don't necessarily like the look of the turbines, and it's as simple as the wind hits the turbine blades. So those big blades you see on the wind turbines are the turbine part of that, right? And as that spins a shaft that's just connected to a generator, and there's our electricity. So there's no heat or steam turbine with our wind energy. All right. This is by far the world's fastest growing energy source because it's relatively cheap. The technology is out there. We found ways to make it work in most areas. And so away that industry has gone. And our newest turbines actually harness wind efficiently, and the great big ones can produce up to 3 megawatts, which is impressive. All right. Where do we see wind? Well, it's most profitable in rural areas. Now, what's cool about wind turbines, and this is happening right here in our valley, is that they can put the wind turbines on agricultural land. So our farmers and ranchers can continue to farm and ranch. And they get kind of a nice little extra paycheck because they lease the space to the power companies. So like Pacific Power, for example, which installs and keeps the wind turbines operating effectively, will often lease space from farmers. So farmers can still farm, they can still ranch, but they can essentially get a little rent check from the power companies who put their turbines on their farm. So it's a nice little win-win scenario. Okay. Now, as far as environmental problems associated with wind turbines, there are few, right? So we need a lot of space for wind in terms of spacing the turbines out. But again, the actual footprint of the wind turbines is small. Probably the biggest critics of wind turbines, aside from fossil fuel enthusiasts, are bird lovers, right? They have been known to show an increase in bird and bat deaths, which is concerning, although they have figured out if they place the wind turbines properly, that's not such an issue. And not so true now, but some of the biggest constraints are cost and public resistance. Just a few short years ago, there was lots of kind of anti-wind sentiment, but wind sort of won that, and you don't hear quite as much hubbub about it nowadays. All right, last but not least here, as far as our indirect solar energy, is hydropower, right? And again, you guys should be familiar with this because this produces the majority of the power in Washington State. Traditionally, that would be done with a dam, right, with a big reservoir. So now we have a large amount of gravitational potential energy. That big reservoir of water puts a lot of pressure. And so to produce electricity, again, this is not a steam turbine process. This is a process of just using moving water to hit a paddle, right? That spins, and that paddle, that turbine, is connected to a generator, and there's our electricity. And the water's discharged out, unpolluted and no problem whatsoever, right? This process right here is by far our most efficient energy source, over 90% efficient. And this is an old technology that runs at about 90% efficiency. So we can produce a lot of power and at a moment's notice because we don't have to heat up water to do this. So some of these dams we have nearby, which are essentially acting like great big batteries. Let's say we have a large demand for power. The turbines aren't spinning very well. We can fire up one of these dam generators in seconds. It's pretty cool. All right. Now, unlike wind, though, hydropower does sort of have some concerning environmental impacts. Now, we generate about 19% of the world's electricity with hydropower. And of course, that's going to be larger in areas that have lots of streams and less in areas like Saudi Arabia, where there are essentially zero streams. Okay. Traditional hydropower is really only suited for these large dams, although new technologies are finding ways to use low flow waterways and much less intrusive methods. Okay. But dams do change the natural flow of rivers. It disrupts migratory fish patterns. Around here, we'd be talking about salmon mostly. And of course, there's potential dam breaks, although in the U.S. we haven't had any major issues with that. We will talk kind of more about problems with dams in a later chapter when we're talking about water resources, but it is worth knowing a few of those at this point. Other potential forms of indirect solar energy, ocean waves, which can only be used on relatively small scales in coastal areas. Ocean temperature gradients too, which is kind of advanced physics to understand that one. But these are just other potentials. I probably won't be testing you on those. Sorry, this got a little long-winded, but we need to kind of cover some ground with that upcoming test. All right, but that covers the first few sections of Chapter 13.